Last time we set up our neural network on paper. This time we'll implement it in the programming language Python. We'll build our network as a Python class, and our init method will take care of instantiating important constants and variables. We'll make these values accessible to the whole class by placing a self dot in front of each variable name. Our network has 2 inputs, 3 hidden units, and 1 output. These are examples of hyperparameters. Hyperparameters are constants that establish the structure and behavior of our network, but are not updated as we train the network. Our learning algorithm is not capable of, for example, deciding that it needs another hidden unit. This is something that we must decide on before training. What neural networks do learn are the parameters, specifically the weights on the synapses. We'll take care of moving our data through our network in a method called forward. Rather than pass inputs through the network one at a time, we're going to use matrices to pass through multiple inputs at once. Doing this allows for big computational speedups, especially when using tools like MATLAB or NumPy. Our input data matrix X is of dimension 3 by 2 because we have 3 two-dimensional examples. Our corresponding output data, Y, is of dimension 3 by 1. Each input value, or element in matrix X, needs to be multiplied by a corresponding weight and then added together with all the other results for each neuron. This is a complicated operation, but if we take the 3 outputs we're looking for as a single row of a matrix, and place all our individual weights into a matrix of weights, we can create the exact behavior we need by multiplying our input data matrix by our weight matrix. Using matrix multiplication allows us to pass multiple inputs through at once by simply adding rows to the matrix X. From here on out, we'll refer to these matrices as X, W1, and Z2, where Z2 is the activity of our second layer. Notice that each entry in Z is a sum of weighted inputs to each neuron. Z is of size 3 by 3, 1 row for each example, and 1 column for each hidden unit. We now have our first official formula. Z2 is equal to X times W1. Matrix notation is really nice here because it allows us to express the complex underlying process in a single line. Now that we have the activities of our second layer, Z2, we need to apply the activation function. We'll independently apply the function to each entry in matrix Z using a Python method for this called sigmoid, because we're using a sigmoid as our activation function. Using NumPy is really nice here because we can pass in a scalar, vector, or matrix. NumPy will apply the activation function element-wise and return a result of the same dimension as it was given. We now have our second formula for forward propagation. Using f to denote our activation function, we can write that A2, our second layer activity, is equal to f of Z2. A2 will be a matrix the same size as Z2, in this case 3 by 3. To finish forward propagation, we need to propagate A2 all the way to our output y hat. We've already done the heavy lifting in our previous layer, so all we have to do now is multiply A2 by our second layer weights W2 and apply one more activation function. W2 is of size 3 by 1, 1 weight for each synapse. Multiplying A2, a 3 by 3, by W2, a 3 by 1, results in a 3 by 1 matrix Z3, the activity of our third layer. Z3 has 3 activity values, 1 for each example. Last but not least, we'll apply our activation function to Z3, yielding our official estimate of your test score, y hat. We need to implement our forward propagation formulas in Python. First, we'll initialize our weight matrices within our init method. For starting values, we'll use random numbers. We'll implement forward propagation in our forward method, using NumPy's built-in dot method for matrix multiplication and our own sigmoid method. And there you have it, a Python class capable of estimating your test score given how many hours you sleep and how many hours you study. We can pass in our own input data and get real outputs. Now, you may be noticing that our estimates are quite terrible. That's because we have not yet trained our network, and that's what we're going to work on next time.